Okay. So far, what I have done is only within the hardware code and have a design within the software code within the software because from technical reason, I have to sort out later on with Professor Jose. But I'm gladly to present my solution, or at least my idea of the solution. So first, I would like to draw a block diagram that contains two parts. The one beneath is the control path, and the one above is the data path. So within the control path, it is just a FSM, so finite state machine, and within the data path, we have three parts. The first part is the UART. RX. So the second part will be the memory. The third part is going to be a decoder. So and there will be a small part in between. I will mention that why I added that later. So within the memory, there are also two sections. One is the memory block, and one is the memory controller. But for a convenient reason, I will just call the both part together as the memory. So what this do is to have connection with your PC. On the left side, when you send out a signal as the UR signal, and for the RX to receive, then you're going to store whatever ASCII code you receive inside the memory, and in the end, the decoder will send out the frequency signal to the speaker. So this looks like a fairly simple design, I would say. I think it's clear, and each part is designated to do each part. So the reason why I mentioned this is that this whole thing can be applied both inside of the hardware and software. So I assume you have seen me drawing somewhat same diagram several times from before. So what I'm going to do now is to use something that we don't like, that is the UML, to address how I'm going to design this. So let's take a look at the diagram. We have, let's say whatever is outside of the two block is going to be the user interface. So we have a user interface here, we have a user interface here. And the memory will be something like, since it's a data path, the memory will be the data, and then here will be a controller, here will be a controller, and the FSM is merely a controller of if you're doing the receiving or decoding to send out the signal. So I wouldn't really go too much detail inside of the FSM. So let's say the first part within the UI as the PC. Within the PC, you will, like, let's say, enter some kind of code like A, B, C, D, E, F, G in big letter and small letter, and then you'll have the UART RX. I would just call it RX. as the controller. And on the right side, I will have the memory block, or in this case, just the memory as data. So in this section, when a user enters some kind of code inside the PC, he can, let's say, this is the notes. So when that was the nodes has been sent into the controller, then the controller can then send out, let's say, write notes. So so this is basically it for the sequence diagram. Isn't it fairly simple? But when we are writing the nodes into the memory, into the data, we have to be keep in mind that we are only having A, B, C, D, E, F, G. So anything else won't be validated. So that's why I have this small block in the middle. This is the validator, which means that in between here, you're supposed to do some algorithm to make sure that the node you have sent out is validated. That is within A, B, C, D, F, G, both big and small letter. So this is the Rx part when you are trying to receive. Okay, I'll draw this too big. So the decoder is going to be somewhat similar. We have the speaker as the UI. And then the decoder as the controller. And memory as the data.
So are you starting from decoder to memory, then also speaker?
Yeah. So within the speaker, let's say we have something. Well, according to Radmila, we're supposed to have something pointing to this part. So I just draw a random line. Please don't tell Radmila about this. All right. So at this part, we're going to get the tone from the memory, and after we get the tone from the memory, we're going to decode the tone. That is generating the frequency. So if you have A, your frequency will be like this. If you have B, then your frequency will be like that. Well, after you decode, you will say send the frequency. So yeah, so basically this is the idea of the design, both in hardware and software. The reason why I designed it like this is that I will, you see, this is UART. It is RX. We had assignment last year in regards to UART. So basically, this piece of code can be reused over and over and over again, and I would like to take that out and reuse it later on because I'm lazy. I don't want to program the same piece of code over and over again, and the decoder as well. So within the decoder, when you receive a node, you will send out a certain signal, so that's fixed. So when you in the future, when you want to design some other robot or anything that you like, with some sound, with some tones, you can use the decoder again. And FSM, also you can reuse it. The memory block, the memory controller, you can reuse it as well. And the only thing that you don't really want, you can't really reuse is the validator in between, because that's only pretty specifically for this task when we are trying to validate A, B, C, D, E, F, G.
Question.
Yes.
So what would you classify the validator? Would you call it a
Well, actually,
controller?
yeah. Well, basically, the validator should be a part within the RX controller. But as I said, I would like to reuse the code over and over again. So I will just take this part outside of the RX controller and do it there, so that it doesn't affect the reusability of the RX controller. So as you can see, we are designing this in a hardware way with a software model, so that we can reuse it.
Please keep in the background of your mind how you are addressing this problem and compare your solution to what you see here, and ask questions to be able to understand the differences if you notice them. For example, you might notice that the ASCII code that is received is not fed into the control path. And in these hints that are available in Canvas, the ASCII codes that are received by the UART are sent to the control path for validation. Now, validation in this solution is done outside of the control path. So if your solution is different, if you do validation in the control path, feel free to ask questions or to.
How did you make that choice?
Just wait a second. I would like to just repeat professor's note, so that it will be recorded on the computer. Of course, the professor's note is that keep in mind why we have the validator outside of the control path, but have it separately with the inside of the data path as a separate part. And your question, please?
Yes, and I'm asking, why did you make the choice to do validation within the data path and not the control path?
Okay, so the question is why I do the validation within the data path instead of the control path. So as you can see, this is actually a pretty standard procedure of a finite state machine with data path. So as I said, I would really like to reuse the code over and over again. So if I take the validator with the inside of the control path together with the finite state machine, that means I'm programming this finite state machine pretty specifically for this task. But however, a finite state machine as a control path can be fairly easy to implement, well, fairly easy to move around in different tasks in regards to if you can just increase the states or some kind of condition of the states, the finite state machine will be easily ported to other tasks. That is validator free, which is not really related to this class. The validator is fairly related to this task that we're doing right now, and which I don't want to see that in another task. That's why I'm having the finite state machine as it is and a validator as it is. Yeah. Any other questions? So actually, I do have a question. I know normally we would like to program in VHDL to make this finite state machine with data path in one piece of code, that is within one big session. But by doing this, you are actually programming the finite state machine with data path with several segments. As you can see, it's quite massive, it's quite complicated and simple at the same time, programming wise. So what's the differences between having the finite state machine with data path programming within segments and within the same scope? Do anyone have any idea about this? Let's say in the regards of the resource we have inside of the FPGA.
Say that again.
So what's the differences between having programming VHDL in several segments and program the VHDL within one whole segment? What, like the differences between having it separately and having it at whole? Do anyone have an idea of the differences between this, Professor?
You are referring to doing it as a hierarchical design instead
Yeah.
of flat design.
Yeah. So let's say in regards to how many flip-flops that we use. Actually, this was a discussion I did last year with Ivan, but I don't think he remembers this. Yeah. So the discussion was like this. He programmed the finite state machine with data path within one segment, and I programmed the finite state machine with data path with several segments. So the difference is when in the end when we're trying to calculate how many flip-flops that we use, we found out that this implementation with several segments actually use like a dramatically more amount of resources comparing to Ivan's implementation, which is programming it within one section. So do anyone have any idea the reason for this? Pezhman, do you have any idea of this? I'm sorry. Okay, so let me rephrase this. With this design, and the way I program, this will be a VHD file. This will be a VHD file. This will be another VHD file. This will be another VHD file, and this will be another one. So we'll have more VHD file, which means that we're going to have more components. So in the end, we're going to have it in the top module with several components and connect the components via signals. So this is what this design is about. And the finite state machine with data path, as I mentioned before, Ivan did is that he only used one big top module. And within that module, he implemented everything that's drawn inside of here, including how to change the states and how you're going to receive the signal with the RX. How are you going to send out the signal with a TX in that case, right? And in this case, it's just with the decoder. So you can see that within his design, there won't be any component being used. But in my design, there are going to be 1, 2, 3, 4, 5, 6 components being used. So did you get the differences between those two designs?
You use many components here, because we are also having 6 components and it's easier to manage. But what he does is absolutely it's really good because it's really hard to track.
Yeah.
If you do everything in one place, it's really hard to track.
Yeah. So, but well, here I would like to say more about the pros and cons between the two different designs. So within the design with 6 segments right here, we're going to use dramatically more amount of flip-flop, and with the design Ivan did when we were talking last year, we're going to use way less flip-flop, which is the resource on the FPGA. So that's the disadvantage about this kind of design. comparing to his design. If you have limited resource, might as well just program inside of one segment so that we use dramatically less amount of resource. But the advantage for this design is that you can reuse each part over and over again in different kind of design. So please.
On this scale of the PGA, a lot of big blocks.
Of course, of course.
Doing this makes it complicated for the large project, but even in the large project, they just package it. I think it's for the scalability, this one is better. If you can just have many components or modules,
Yeah.
and customization is much easier.
Yeah, well, that's what I'm saying here. The customization is much easier, but it depends on how much resource you have. Right? For in our case, we have enough resource to implement this, so I think we can use this to make it easier to take an overview. But if you have dramatically less resource, then it would be nice to have it in one segment. Yep. So that's my introduction here.
Sounds like it's essentially you're finally leading to a co-design question about performance and use of resources.
I'm sorry, can you?
I'm saying your question reminds me of what we read for co-design Object 1.
Okay. I'm not exactly sure what you're talking about. So.
Where you're designing the hardware and you're thinking about fake flops and
Yep.
use of the resources, and you're also considering about using components and being able to come up with new designs. That being able to come up with new designs using pre-made components reduces the time to make a design.
Okay. So Ethan was saying that this kind of design actually reduced the time for the designing.
And probably makes it easier to fix errors.
Yeah, and makes it easier to fix the errors, which I believe so as well, because you can then do simulations on each component to limit down how many errors you have. Yep.
Yeah, but I guess that Joe will also consider an advantage of doing it in this way, because you can look at the UML model and find out a way to devise how to build this prototype in software and in hardware and compare it.
Yeah.
As you are going to talk about in a moment, by implementing each of those blocks a certain way when it comes to the software.
Yeah, the professor mentioned that the way I programmed this is to have it compared with the software, which is basically true. This is exactly the way I program both in hardware and software. So basically saying that each components we have here can be regarded as a class. So when you have a class as the UART RX, then you can just have a class here and use it as a control. Without. So by looking into that, you can say we have a class as the UR, or in my case, the RX, and then you will have a constructor, destructor, and then you can have some function, for example, like receive or read, note, store, note. So those are basically the function that you're going to have inside of the RX, and then also you're going to have a class as decoder. Also the same with constructor and destructor. Then you have the read data, let's say read data, and generate tone, and then send tone. So then you will have two classes comparing to the component inside of the hardware, and the memory will just be basically a memory, and the UI is the signal that you're going to send out, or which is is just the user interface we have here. So so the comparison between the VHDL and C++ could be quite obvious on which segment is for which functionality, and you can compare the code you have in C++ and a VHDL to make it, pretty vivid for you when you're designing stuff. Yep, that will be my introduction of my idea, and please criticize me if you have any doubts and questions, or you see anything that's improper.
And you would like pick some right. What's underneath constructor? I didn't follow.
What's on?
RX.
Okay, yeah, RX constructor, you have the read node, that is, you have the node read from the user interface, and you have store node, that is, store the node into the memory. Of course, you can also have a class as the validator, or just basically a solo function called validate. And you call this function when before you store the node. So yeah, so you have the validate as a separate function to make this here reusable. And the node can be basically anything you send out. Like you're trying to, for example, when you're trying to chat with something via UART, which is quite a weird way to do it, you can just reuse this module and have another class as the TX, and implement with integration between the RX TX. Then you can actually initiate the chat between someone else, you and someone else. Yep. I guess that will be all. Thank you.